Okay, great, great. So excellent. Now, today we are going to talk about the probability and the random walk, and then gradually we will talk about the getting into the topics of diffusion. Okay, so this actually is a very important fundamental topic in the biophysics, and it's very very interesting, and many interesting mathematical derivations contained in this section. So before we talk about this, a few logistical updates are here. Firstly, I received your homework #1 solution. I think all of you are doing great job. That's great. So I put the complete solution for homework #1 on the canvas now, so you can check the answers. But qualitatively, if you do well, if logic is correct, then I think you're doing great. Okay, so then you get all the score. The final quantity is not that important. The importance is the process, the logics of the problem solving. Okay. For the homework #2, I added we have that posted already, and it's due middle October. So take your time to do the homework #2, and we also have MATLAB tutorial uploaded, so you can use the MATLAB in the computer lab, or you can use that online. MATLAB also has an online version, so you can log in, you can register an account, and then use that software. Okay, so that's very useful. It's a very good scientific software to perform the mathematical computations. This Friday we will have the midterm exam #1, and we have the example questions already uploaded. So feel free to use that to get yourself familiar with all the concepts, and then use that and then review all the concepts we discussed in the class. Okay, the exam will contain 10 questions, and those questions will be in the same format as the sample question I uploaded. Okay. Last but not least is I put some new reading onto the canvas. Those reading actually are related to our today's topic. They are the diffusion and the random walk paper, originally paper by Albert Einstein, and then some important concepts about the statistical mechanics. So you can read those papers. Those papers are very very good, and you can use that to appreciate how they derive equation, how they convert phenomena into mathematical descriptions, and then from mathematical description get the physics insight. Okay, so those papers are very good. I will also upload some papers by Dr. Brown, Robert Brown. So he is the person discovered the Brownian motion. Okay, he also has the original paper. I will put that onto the canvas so you can read them together. Okay. Okay, good. And then feel free to send me your survey. And anytime you send me the opinion and survey, as many of you actually have been doing, that's great. So I will use your feedback to help improve our class. Okay, this will benefit all of you. Good. That's all the logistical updates. Do you guys hear me? And do you have any questions?
Yeah, Dr. Tang.
Yeah, please, Daniel.
In Canvas, you said the test was open note and open book, and it says it there as well. By open book, what do you mean?
I mean that all the reading, right? In a reading, we have many books, right? Reading. So yeah. So what I mean is I don't have any restriction. You can use anything in any resource in your hand. What I want is you understand the concepts we discussed, and then really can use those concepts to solve any scientific questions. That's all I want.
Okay. And I think last lecture you mentioned that this exam would be taken in class. Was that over Zoom, or are we actually going to be physically?
Over Zoom. Okay. Over Zoom. Yeah.
Okay.
I put the example question into the Canvas folder, right? So in the Friday, 3 p.m., I will put the midterm exam question also in the same folder, and then I will be on Zoom. So either I or my student will be on the Zoom. So then if you have question, you can ask me.
Oh, okay.
Good. Good. Thank you.
Will we just like scan our answers or type them or whatever, and then
Yeah.
email it to you or post it on Canvas?
Just email me too. It's fine. Yeah.
Okay.
It's most straightforward way. I don't want to waste your time to figure out which method, use different method. Just one method. Just email me. Yeah. Save your time to do the good research, good study.
Sounds good. Thank you.
Excellent. Excellent. Jackson's very good. Any other questions? Okay. If you have any question later on, you find out, just let me know anytime. Okay. So I want to make sure that all the logistics are super clear. So then you concentrate your energy, your time into the meaningful study and your own research. Okay. Very good. Very good. So now let's start today's lecture. So here is the outline of the whole class. Right now we finished the basics of life, and we are all on the same page, including the engineering students who have mechanical engineering students or the other physics students who have not who are not very familiar with the fundamental biology. Okay, so we have gone through all the basic concepts needed in this class, biological concepts. Now we are here. We will talk about the mathematical derivations of probability theory, Brownian motion at the micrometer scale. And then we will go to the macro scale talk about the diffusion and correlation and the kinetics, and as well as their applications. Okay, so we are right now in a good timing. So just follow me closely, and let's start this topic today. Okay, so Brownian motion. So this term, I believe many of you heard this term before, Brownian motion. This actually is a very fundamental process in the micro scale, okay? And in the cell, this actually is the dominant mechanism, or it calls default option for any small entity, small things to move around in the micro scale, to move around inside the cell. We're talking about the motor protein that it can work deterministically around one direction on the microtubule or cytoskeleton, right? So that is a deterministic process, and that takes ATP, takes energy. Brownian motion is a different way for small things to travel in the cell in parallel to the motor protein. But Brownian motion is not in one direction. It's actually moving around. It will scan through a lot of different locations, and then finally achieve the destination, arrive at the destination. So it seems is random, okay? But the good thing is that it does not cause energy, does not cause ATP. So it's a very it's an energy-free process. Okay, so that's why any small entity, they actually can do the Brownian motion. So this is a default option. Okay, but why the small entity can do this Brownian motion? That's actually the things very interesting. So, and we will do the mathematical derivations to learn more about the Brownian motion, and also to quantify what kind of important theory and laws we can learn from the Brownian motion. Okay, so let's do that now. So first of all, I have a question for you. Have you seen this kind of toy previously called Galton board? Have you seen this kind of tools before? So this actually is the tool that are always in the museum, always displayed in the museum. At MIT, if you have been to MIT, in the Kindle Square, in the Kindle Square, they have one just inside of the subway station. So they have this machine, and this machine actually contains two parts. The top parts contains many pins, horizontal pins, and then bottom parts contain many isolated but connected parallel beams, and inside of them there are many balls. These balls can be put together on top. Do you see my mouse? Do you guys see my mouse?
Yeah.
Yep,
Yeah.
we see it.
So those small balls actually can be put at the center. You see the center, there is a small outlet here. So all these balls can be put in the center and then let it go down. They all start from this center region. And then whenever they come down, they bump to the horizontal beam. And then the beam blocks its way to go straightly down. And then the ball will have two options. One is going left, one is going right. Okay. And then they go and then fall down another layer. And then they will bump to another horizontal beam and then make another two options. And then keep doing it. And then they will be collected into those vertical beams. And then each beam actually is isolated from each other. Okay. So then any ball falling into one beam will be staying there and will not go to other place, will stay there. Okay. And then after that, after all the beams go through those process and then be collected in those beams, then you can see the pattern. You can see the pattern, how they distribute in each beam. And then here people can open this bottom bar and then collect all the beam. You see this is going down, right? So using gravity, they can recycle, collect all the beams again, recycle it, and then move up, all the way up, back to the center, and then release it again. Okay, so people do this experiment continuously all the time. And the interesting thing is no matter how many times they do this experiment, the final results, the final distribution of the balls inside those beam always show this kind of curve. Center always has more balls collected, and then gradually decay. Okay, at the edge they collected less. Okay, so this one is called this tool is called Galton bot. Okay, and then this distribution actually is called a normal distribution, called a Gaussian distribution. Okay, so this whole process actually can be explained by mathematical derivations, why they show this kind of distribution constantly. And this mathematical theory that behind this phenomenon happens again and again in nature. Later we will find why it happens again. Okay, if we have time, we can do a proof. Okay, I'm not sure whether you have seen those devices before, so I'm going to play a video, then you can see. So here's a video showing that this is a smaller device, smaller version of the Galton board. They can work on the table. So then they using those balls, put those balls, small balls, in the center, and then they will fall down. They will bump to the horizontal beams, and then finally show a distribution at the bottom. Okay? So let's watch this video together. Okay, so they recycle it now. Do one more time. You can see every time it follows that distribution. Good. Yeah. Can you see the video? Can you guys see the video?
Yep, we can see
Yeah.
it.
You can see. Very good. Very good. So this actually is a particular is just a one specific case about the nature selection. Okay, it's one specific case. if you look into the mathematical background, mathematical foundation of this, you will find the theory about this phenomenon is the same. It's the same. Okay. If I change the number of those horizontal bars, or change the position of those bars, the ball, when they fall down, they will have different selection. You have different selection. Okay. Then interesting thing will be, finally, if you do as many times as possible for those balls, they eventually will still form this normal distribution, form this Gaussian distribution. Okay, that is a physics theory. That is called a central limit theory. Okay? And that theory is one of the three pillars of statistical physics, and that it can be found universally valid in many nature phenomena. Okay? Some phenomena might be because of electricity, some are because of magnetics. Okay, but they are fundamental mathematical foundation is the same. Okay, so we will use the Brownian motion as one example to show the application, to show this mathematical foundation. Okay, but there can be other phenomena as well. So the Brownian motion I mentioned multiple times. Brownian motion actually was discovered by Dr. Robert Brown. He is a British botanist, okay, a scientist, and he actually has his own garden, and he studied the plants, flowers in his garden, and then do the biological study there. Okay? And he actually not only do the theory work. Okay, he also do the experiment work, and he can use his hands to construct microscope, and use microscope to see more detailed items, detailed entities in the plants that are beyond that cannot be distinguished by our naked eye. So one day, Dr. Robert Brown used his handmade microscope to look into the water close to the flower, and then he finds there are many pollen grains. They are coming from the flower. Actually, it's mixed into the water, and then he finds something really interesting. He finds those pollen grains. They are actually at the size of a micrometer scale. They actually move inside the water. They are moving frequently, okay, and then he did a series of experiments to verify to answer a series of questions he asked. Okay, I will show you what question he asked. Okay, to dissect what's the mechanism of the movement of the pollen grains in the water. Okay, and then he published what he discovered into this original paper. At that time, in this paper, he drawn a final conclusion. That the conclusion is those pollen grains are moving inside the water, not because those pollen grains are alive, but this moving phenomena actually is general. Even he took the small particles that's not from the pollen grain, some even non-living small particles. If he put it into the water, he can see the similar pattern of movement. Okay, so he reported that into this paper, and then this phenomena actually is very useful. At his time, people already have the concepts of molecule. People think everything is made of molecule. Okay, and Robert Brown at that time he claimed he found the molecule, but that part is wrong. That part of the conception is wrong. Okay, because the particle he used is still thousands or tens of thousands larger than the real molecule. Okay, but the importance of this paper and his observation actually is is that it provides the first evidence to help people to link microscopic world to the microscopic world, because the movement of those small particles can actually be mathematically modeled, and then that mathematical model can be used to link the movement of water molecule, and the water molecule you cannot predict, you cannot see at that time, but you can predict, you can derive its movement, and then that movement, when you assume water molecule is bumping to those micro scale molecules, then the mathematical derivation is very consistent. So that's actually the importance of his observation, that links macroscopic world to the microscopic and even nanoscopic world together. Okay, so that this observation is super important. So here is what Dr. Robert Brown stated in this milestone paper. Although part of the conclusion is wrong, but the phenomenon is correct, and this phenomenon give people very important observation and insights. Okay, so he said, while examining the form of those particles immersed in water, I observed many of them very evidently are in motion. Okay, so this is very important. So let's see what is the thing that Robert Brown observed on the microscope. What he sees is something similar to this picture. Okay, this video. Do you guys see the video?
Yeah.
Yeah. Good. So in this video, actually, there are many fluorescent beads. This is the fluorescent bead. So fluorescent beads is about hundreds of nanometer, 500 nanometer to 800 nanometer. Okay. So if you put those beads into the water is not fluorescent. So there are no light coming out. The only light is coming out from the fluorescent light when they are excited by the excitation lasers, right? So you see the movement of all these fluorescent beads around, very energetic move around, right? So Dr. Robert Brown observed a similar thing on the microscope. He observed a similar thing, and then he wanted to know why those things are moving. So he asked a series of questions and then answered those series of questions by himself by doing the experiment. Okay, so firstly, when the Robert Brown saw this called juggling. Okay? At that time, he used the word juggling widely in the liquid. He asked a logic series of questions, and then to perform the experiment to address that. First question he asked is, are those grounds he used alive and swimming? Because based on the Newton's law, that anything when they move, they have to have some force applied to it, right? So if these grounds are alive, then maybe internally they can generate some force and then migrate and then move and then swim, right? So that's his first question. Then he actually tested. He took some pollen grounds that is from the plants that has been died for 100 years, a century ago. So that ensures the pollens are dead. Okay, and then he put this definitely dead and those ancient pollens into the water, and then observe again using his microscope. He find that they also jiggle. They were also jiggling. Okay, and then second question he asked is this movement, because he only tested the pollen by now. So he asked, is this a special property of the pollen from the flowering plants? So then he tested he first used the flowering plants, okay, and then he tested other kind of pollen from different plants, like from the moss. If you visited England, you know there are many moss, right? They use the moss to organize many mazes, right? So this is the sample he can obtain very easily. So he tested the pollen from the moss, and then he found that there's another type of pollen also jiggle. Okay. Then the third question he asked is this motion property are special property of pollen from onion plants. So then he tested a series of different material, a material different from the pollen, okay, such as including many small pieces, even a small piece of the sphinx. That is the oldest and deadest thing he could find at that time. So sphinx is from Egypt. Is this one? He took a piece of a sphinx and then make it be very small particles and then put it into water and then observe that. They find that they also check it. They also check it. Okay. So then Dr. Brown drawn a final conclusion. He named this motion as a Brownian motion. And then he claimed that this Brownian motion is a fundamental property of all microscopic divided matter immersed in water, because he finds it seems only this Brownian motion seems only related to the size of the particle he used. Doesn't matter what the types of a particle is a size. If the particle is too big, like several millimeter, hundreds of micrometer, okay, then they put it in the water, they will stay there, not be able to check that frequently. Okay, but if the size reduced to the 1 or 2 micrometers, even smaller, then they can be very obviously observed to move, just like this. Okay, so just like here, when we put the fluorescent beads into the water, we can observe those motion, and we know that the fluorescent beads are not alive, right? So this is a very interesting phenomenon. Why those small things, small particles can move without adding the energy to it, without being adhered to any living things. Okay, why they can do it? So, in fact, this phenomenon exists in nature very universally. If you take any water, you will see any small particle in water. You will see they actually move, and this movement is every particle. If you treat it as like a kit, then if you look at the piece, look at the drop of water, you will find that inside that drop of water, it's like in a kindergarten. All the particles are like the kids running around crazily. Okay, they do not have any directed direction, and they all move without stopping. Okay, so after the publication of Robert Brown's paper, many people wanted to understand the reason, the mechanism of the Brownian motion, but only that mystery persists for about 80 years until 1905. That Albert Einstein, he published 5 papers in that year, and one of the papers actually explained the physics and physics origin and mathematical derivation of Brownian motion. And then he in his theory, he explained beautifully that the Brownian motion actually is a consequence of the thermal motion of the molecule of the solvent. Okay, so he actually, he actually explained it's because of the thermal motion of water molecule in the solvent that it bumps to the small particles immersed in the water in different directions at different times, and then that result in the observable motion of the particle under the microscope. Okay, so I added the Einstein's original paper on the canvas now, and then you can see, yeah, here is actually a Germany version. I put both Germany version and the English version there, so you can read that. Okay. So
I have a question.
Yeah, please.
So does the Brownian motion only apply in water, or could it also apply in a gas?
In a gas is not very obvious. It's not very obvious because the gas molecule density of gas molecule is much lower than the water molecule in a liquid.
Okay.
It can happen, but not that obvious. Okay, and you ask a very good question, Eric. Excellent, excellent question. It's not restricted to the water molecule. It can be other molecule as well. Any molecule at the nanometer scale, they can have a thermal jacketing. And then this jacketing can apply bumping force to the particles within the solution. Okay, that can cause the random movement. And then that random movement, by definition, is also Brownian motion.
Okay, thank you.
Sure, excellent. Yeah,
I've got a quick question as well.
Yeah. Please.
So when because I haven't learned about Brownian motion formally before this, but when I first heard about its general concept, the first thing I thought of was like molecules forming instant dipoles with one another, and that causing instantaneous motion because they get force from electrostatic interactions. Is that kind of the origin of the forces causing Brownian motion?
No, it's mostly caused by the physical bumping. So if you have you can imagine that you are going to a train station. You go to the train station. There are many people there, and then you stand statically in among many people, and then every people going past you will bump to you, and then you will move, right? You will be bumped by many people, and then you will move, right?
Okay.
That kind of movement. Imagine that the water molecule is bumping to the particles, to the pollen grain.
Ah, okay. Interesting.
Good.
So, hold on a second. I'm trying to get a thought out. Shoot, I just lost it. I'll ask a little bit later because I just lost the thought I had.
Yeah, anytime, whenever it comes back. Yeah, good. Okay, so now we can calculate some of the Brownian motion's consequence. So some characteristics about the Brownian motion that are very useful we need to know. So Brownian motion actually occurs at the thermal equilibrium. At the thermal equilibrium means there are no net energy gradient. So this is in the thermal equilibrium. Temperature is the same everywhere. Okay, and then in that condition, we assume that there should be no movement, right? Temperature is the same, but the molecule, small molecule, at a given temperature, they can still jiggling around, and then those jiggling around can bump to the particles. That gives rise to the Brownian motion. Yeah, and in terms of the life in the cell, actually in the cell, actually we are not at the equilibrium, because in the cell temperature is not uniform, and also we have a net free energy generated by the cell, provided by the ATP or other means. Okay, so the life is actually not in the equilibrium, but the Brownian motion occurs in the non-equilibrium condition as well. They can go in parallel. Okay, but the important concept is life is not at the equilibrium, and if life is at the equilibrium, means there are no free energy existing in the cell. Then that cell will die. The cell cannot do any work. Okay, cell cannot survive only by doing the Brownian motion. They also needed the free energy for them to drive motor proteins and drive other process in the body. Okay, so that's a very important understanding we need to know. Okay. Also, Brownian motion is the dominant mechanism by which that the small things move around, because they don't need this motion does not require free energy, does not require that. So they can do just in the solution. Okay? So in the living cell, the Brownian motion is the default option for many molecules to get to travel from position A to position B. Okay, and of course there are here I ask another question. If molecule in a cell want to travel from position A to position B, are there any other options? Of course, there are other options, such as the motor protein can help them to achieve the travel. Right? So to identify, to see that to see the Brownian motion, to categorize that any motion is a Brownian motion or is actually carried by the motor protein or both, then we can study the trajectory of the particle as a function of the time. So there's so here you see this red curve. This curve actually is showing can be generated from a video. So in each time of each frame of the video, each time you can get one frame, and then at that frame, the particle starting from here, you can find its position, and then in the next frame of the video, you find the particle move to another position, and then and so on. They go to many positions. You record the position of the particle, and then use a right line to align to link them all of them together. Then you will get this kind of trajectory. Okay, it is this pattern. From this pattern, you can measure, you can calculate that by measuring a term called a mean square displacement. We will talk about this in the next few slides, but I just want to give you a heads up first. So you can calculate from this the distance. You can do a calculation. You can do a mean square displacement of this, and then plot that mean square displacement as a function of time. Okay, as a function of time. That time you can also rewrite it as time distance. Time increment means that between each frame, what's the time difference between the frame? Time 1 and time 2. Time 2 minus time 1 is the delta t, is time increment. Okay, and then you can change time increment, and then calculate the corresponding mean square displacement (MSD). If the MSD versus delta t relationship is linear, if the relationship is linear, that means this movement is a Brownian motion. It's a really Brownian motion. That means the particle is in the thermal equilibrium. Okay, so the motion of particle is solely driven by the bumping of the water molecule, and in a random way. And there are no temperature gradient. There are no free energy gradient. Okay. Now there are several exceptions, not exceptions. Several particular case you always will find in the real experiment. B and C shows the difference. B shows a different one type of Brownian motion called a confined Brownian motion. Brownian motion also called random walk. Okay, so the particle is working in a random way, so we call it a random walk. But in a cell, because the cell has a specific boundary made of the lipid, right? So the particle cannot go everywhere, so it can only stay within the cell body. Okay, so in that case, if you calculate the particle cannot go outside of some domain. In that case, if you calculate the MSD, mean square displacement of the particle, and then draw its relationship versus time increment, you will find that at a small delta t, the relationship is linear, but at a larger delta t, they will go flat now, will reach a pattern. Okay, that is because at a large delta t, this particle will keep bumping to the boundary and then come back. So the net displacement is not increasing; it's actually decreasing. Okay, so they cannot increase the displacement anymore after the particle encounter the cell membrane. Okay, so you see this curve goes like this way, and it has maximum MSD around here, right? So it cannot go even further. Also, if you look at the particle in the cell, they actually, as we mentioned, the cell has many compartments, right? Made of the membrane, or sometimes made of lipid membrane-free protein organelle, right? So they can actually move and then get constrained inside of organelle. And then once that organelle released, then the particle can go outside. and then go outside, they can get into another particle, another organelle, right? So in a real experiment in a cell, if you have particle, you can see mostly condition B, condition C. Those in the C, actually, what you will observe is many small confined random walk process linked together. Many small, those curved lines linked together, because of the particle will be confined in one organelle, and then released and go to another organelle, and then go to the bigger cell, and then encounter the cell boundaries. Okay. Now, in a real experiment, once you see this, they are also belonging to the Brownian motion. Even their curve not the same as the theoretical curve, that is linear. Okay. This actually tells you the theoretical part is valid at the beginning, the linear one, but really there are boundaries due to the cell size, and then the curve will go curve. This involves both the Brownian motion and the confinement of the boundary. Okay? So you will see both cases, and by analyzing those curves, you can find many important information, such as the viscosity, the property of the environment. Because the property environment, if it's very viscous, or if it's not viscous, actually will make this displacement to be smaller or to be larger, because of viscosity can drag those particles. So by analyzing those particles in different location of the cell, you actually can measure viscosity and mechanical property of that region of the cell. You can measure that in the nucleus or in the organelle or in the cytoplasm, whether the liquid viscosity actually change, and also whether the environment is crowded to apply the confinement frequently to the particle. Okay, so those information, many of them are actually very difficult to measure by specific tools. Okay, but if you understand the Brownian motion well, then you can put the small particles in the cell, and then you can derive those information to get the first hand understanding. Okay, so we said, do you guys hear me?
Yeah.
Yeah, excellent. So we said that the Newton's law. So here actually shows Newton's three laws. So we said that in the Newton's law that the Newton's law explained the principle of motion at the micro scale and macro scale very well. Okay, but every physical law has their valid range. It cannot be valid in every spatial scale. Okay, so if we are talking about the cells and molecules, we have to go to the micro scale, nano scale. At that scale, Newton's law is not that accurate. Okay, at that scale. So at that time, yeah, as I said here, the range of validity of Newton's law. Newton's law applies best to a microscopic object, okay, in the region of the low friction, and they provide a very good way to calculate the motion of planets, cannonballs, and falling apples. But at the micro scale, at the micrometer scale, the Newton's law are not the best language to use, and also at the quantum scale. At the quantum range, people study the relativistic particles that are close to the atom, okay, close to the atom and close to the electron. Newton's law also are not the best language to use. We need to use different physical laws to describe them specifically. Okay, so now Brownian motion is at the microscale, so we need to derive the mathematical foundation of that now to totally interpret why they show this kind of behavior. Okay, so now next we will go through the mathematical factors to especially probability distribution that can be very useful to help us understand the Brownian motion, and then we will calculate the consequence of the Brownian motion. And finally, we will learn the macroscopic diffusion that comes from, that rooted from the Brownian motion. And then we will give some examples. So this is the topics we will cover in today and the next few lectures. So first, let's go through the probability distribution. This mathematical derivation actually is very, very useful. You can use it to analyze many things in the lab. Okay, so they're fundamental but not trivial. So please follow me closely. So let's first consider a small particle can move, and then it moves by taking steps. So at each given time, it take one step and then move forward or backwards. And it is a 1D movement. It goes around x-axis. Okay. So each time, so if this particle is moved in a way that it will need to make decision, how big is the step size? They need to make this decision. Then the step taken by the particle can be described by a probability distribution. For example, on the right-hand side, you see a diagram. This diagram, it shows a probability distribution. It shows that the x-axis is the size of the step that the particle can take. It can take a step size vary from 0, so the particle will not move. Okay, and then it will all move size 1, or move size 2, or move size 3 towards positive x-axis. If the particle go negative, around negative x-axis, then it go -1, -2, -3. And in each step, when they take, they actually has a chance to take. So the largest chance is at a small size, because the particle may want to save some energy. So at any given time, the particle may have this chance between 0.1 to 0.11 around here to stay in the original position. And then if particle take a step at the size of 1, that chance is about here. It's about here. About 0.7. Okay. It has a 1.7 chance to take a step with the size 1. Okay. And so on. So at the different steps, they all have corresponding size that is reflected by the y-axis. That term is called WS. So that is the probability for each step taken by the particle. Okay, and this WS is called probability distribution. Okay, if we integrate all the probability distribution as a function of each step size, you integrate them together, you get the number one. Okay, so this probability distribution is giving the distribution of one possibility, only one that possibility as a function of different step size. Okay, if we summarize my explanation into a mathematical equation, that will be this equation. It's an integration equation. So the WS, the probability distribution, that is as a function of S, different step size. If I change the step size from -infinity to positive infinity, means I take all different types of step size and then multiply them by their corresponding probability distribution. Then overall, it summing together, I will get a 1. Means the particle will take a one-time move. Okay, we get a 1. Okay, so that is the description of this diagram. Now this term WS, this probability distribution, has finite mean and finite variance. Okay, so these two are very important terms to understand what kind of probability we are using. Okay, By the way, this WS can be any kind of mathematical formula, okay? Depends on the physical nature. It can, sometimes it's not a distribution. Sometimes it's a line, it's a vertical line. It can be a delta function. Means the particle can only take one kind of step, and it can only make the size, make a step at that size. And that size is at that point that has a vertical line, vertical delta function. Okay, and then even that case, if you integrate delta function across the range of S from negative infinity to positive infinity, you will also get 1, right? Based on the mathematical definition of delta function, right? So all what I'm saying is WS can be any function. Okay, so this is generally correct. Okay. So right now it's 351. So let's derive more useful mathematical parameters of WS in the next section. It's Monday. Okay. So I will see you Friday to have the midterm exam first. Okay. Thank you.
Dr. Ting, I had a question really quick.
Yeah,
So
please.
for